Welcome to Amber Book 40 Minutes of Competence. This is Michael Ermann, and today we're going to be talking about parapets. Parapets were originally they were designed or included in buildings so that the fire from one building wouldn't spread to the other buildings in the area. You know, when you read the history of 18th and 19th century American building, it's just fire after fire. Conflagration that just swallows cities whole. So the idea of having a wall that kind of wins when it meets the roof was one way, especially if that wall was masonry, was one way to prevent or make it less likely that the fire would then jump to the next roof. We also did it so that the wind forces that are what we have is we have a situation where historically these were used to prevent fires and to make it so that the wind forces that are going to be going, kind of this way, didn't peel up the roof membrane, so as to protect the edge of the roof membrane. I would also add that something's got to win. Either the roof has got to win, like this. This is the architecture building here at Virginia Tech, and I think it looks a little goofy when the roof wins on a tall building. But it does protect at least the top portion of the wall. It's more likely, you're more likely to see the roof win on a smaller 1 or 2 story building where the overhang can actually do some real protection and where it doesn't look quite so awkward. And it's kind of the defining feature of that particular building. And then on the wall wins, this is the next building over, and just about every big building, the wall wins when it meets the roof. If they don't, and it's not limited to low slope roofs, it can be a flat roof that has a parapet. And if you don't have either one win, if kind of one ends at the other, you wind up with water damage or staining coming down and starting to do some bad things. Now, sometimes we really like the look of that kind of edge, and it's fine if it's in a dry climate, but if it's in a wet climate, it's likely to at least stain and possibly rot or mildew or mold. There are ways to deal with that, though. If you want it to kind of hit the edge, like this Arius Mateus, aren't they fantastic? Building in Portugal, you can integrate the gutter into the actual roof. And the problem with that, though, of course, is it redirects the water so it's not going to stain this beautiful white roof. But the problem with that, my parents have an integrated gutter, and gutters leak all the time. You've seen this a million times, and when that leak happens to be integrated and above the wall and you don't know where it is, it causes reasonably significant amount of damage kind of often. So I don't know, I feel like there's a design solution for it. I just don't quite know what that design solution is. All right, so we need to do 4 different things. We need to keep out rain, we need to keep out air, or keep in air, both. We need to keep out cold, or keep in cold, or both, depending on the season. And we need to sufficiently handle vapor. So let's start with rain, because that's the most important one. And so we're gonna have, in this example, we're gonna have a flat roof, or really it's a low slope roof. It used to be called a flat roof, kind of, when you didn't know about architecture. But we're going to have some kind of a membrane roof in this example. All the things we're going to do for rain, I'll just do in blue. And we're going to allow for a slope on the roof. The slope is going to be at least 1 to 50. That's what the code requires. And then every so often we're going to have at a low point, we're going to have like a little screen and a roof drain, and that roof drain is going to take the water from the roof somewhere else. And then because we have really 3 tools available to us when we're dealing with water. One is kind of, I don't know, we'll call it plastics and continuity. The idea that if you have something that's kind of plasticky or metally, and there's no holes in it, you're not going to have a leak. You're going to keep rain out that way or water out that way. The second is the idea of lapping, and the third is the idea of a drip edge. So we'll use all three here. Now, you might be tempted historically, you might be tempted to say, well, let's just run this membrane, this roof membrane up here, over here, and down here, because we generally want to run it at least 4 inches down. We want to run it at least 4 inches down because that allows us to make sure that wind-driven rain isn't kind of blown up into the under the kilt there of the membrane. And that would seem like a good idea, except roofs get really hot and roofs get really cold. And even though they don't expand and contract a lot, because they're often big and because the temperature can easily swing from well below freezing to near the boiling point of water on the roof membrane itself, it is likely or liable to shrink. And if it shrinks, what's going to happen is it's going to pull, it's going to kind of overturn this brick. So what we're not going to do is we're not going to run it continuous. We're not going to be able to. So let's figure out a better way to do it. So what we're going to do instead is we're going to run it up just a little bit here. We're going to kind of turn it up here. Oops. And then we want to make sure that any water that actually falls on top of the parapet itself, we want to make sure that that water is directed inward, because we don't want it to go outboard because it'll stay in the front of the building. So what we'll do is we'll kind of build up something with a slope here that looks something like this. And then what we're going to do is, back to kind of thinking about water, what we're going to do is we'll lap that turn up on the roof, that roof turn up there. We'll lap it like this, and we'll have a second waterproof layer that's going to lap it. And then, because we don't usually want the waterproof layer to get a puncture or something like that, we're going to cover it. Now we might cover it with stone, or precast concrete, but that doesn't do the job by itself. We need this, this kind of waterproof layer that I just drew, because well, first of all, stone is sometimes porous, concrete's always porous to water, and then even if it is porous, you have the gap, you have that kind of a gap every 4 or 5 feet where you have caulk, and caulk sitting in the sun and in the rain horizontally indefinitely, there will always be eventually a problem. So we'll put a piece of metal, and we'll use a drip edge so that it doesn't drip down on the wall, and we'll use a drip edge so it doesn't drip down on the inside parapet, and that's how we'll keep water out. That's how we'll keep water out of the parapet itself. Then we'll run some kind of a waterproof layer, a rainproof layer, right up against the sheathing or the enclosure of the building. And that could be a peel and stick membrane, that could be one of any number of things. It could be lapped, or it could be lapped tar paper, it could be lapped Tyvek or polymeric house wrap. But in our case, we're going to do a fluid applied. It could be roll-on or spray-on. It's kind of like truck bed liner, like that stuff you see that protects the bottom of a pickup truck. So it's going to be sprayed on, and maybe we'll turn it over a little bit just so there's a little bit of continuity here. And that's going to be our true waterproof layer. Now, in practice, the way it's going to work is rain is going to come here, and it's going to mechanically hit that wall, and it's going to drop down. Maybe 99% of the water that would hit the wall is just going to mechanically be shielded with the brick, and then maybe 1% of the water is going to go through But of the water that goes through, 99% of it is going to go down in the cavity and be taken out by weep holes at the bottom, and flashing, redirected by flashing and taken out by weep holes at the bottom. And so that's most of the rest of the water. But that's 99% of the rest of the water, but there's still going to be some water that for some reason works its way all the way through to the enclosure. And we really don't want our wall to leak rain. And so what we're going to do is we're going to use that bed liner product, and it's got to be pretty perfect. We want to make sure that any water that would otherwise get in there cannot get in there. So we have a three-pronged system. One that relies on what's called mass, kind of the ability of the exterior surface to absorb water and mechanically deflect it. So it's a mechanical layer. That's the first one. Our second one is the capillary break, the idea that anything that goes through is going to drop down. And our third one is the true waterproof layer. Now, this is going to get a little confusing for a couple of reasons. And one of the reasons is that a function like rain or air or thermal or vapor, each one of those may require a separate layer, or one layer, one specific building material might handle more than one of these. So keep that in mind as we go. Now, if we turn off the actual building, you see that we have a continuous layer, that if there was rain falling from above, you can see that if it's done properly, none of it should get into the cavity, none of it should get into the building, either through the roof or through the wall, and any that does hit the waterproof layer should have a place to go. So we're okay there. All right, now I'm going to turn off the waterproof layer for a second, and our second task is to make our building airtight. And it turns out that it's not unusual for some buildings built today to be 20 times more airtight than other buildings built today. Airtightness is one of those things where a little bit of design knowledge and a little bit of detailing and a little bit of construction oversight can actually go a long way to making your building a lot better than your last building. And so one of the things we're going to do is we're going to, if we want to make it airtight, we're going to put an air barrier down. Now, wasn't this guy right here an air barrier? It's a roof, it's a membrane, air doesn't go through it. That is true. It is itself an air barrier. However, we're going to put a second air barrier down underneath the roof. And more on why that is later, but just kind of keep that in mind. All right, so we have, let me get rid of that. We have, if we're going to put an air barrier down, the first thing we want to do is, it's hard to put the air barrier down right over the kind of flutes of the metal pan. And so we're going to have this little thing right here, this enclosure board. It's maybe exterior rated gypsum or something like that. And on top of that, we'll do all the air barrier stuff as green. Maybe I'll make it a little thicker so we can see it better. And we're going to have an air barrier above that enclosure. And we're going to take that air barrier and we're going to run it up to make it continuous, because just like the rain barrier, the air barrier wants to be continuous both in plan and section. And what that air barrier is it's going to be, it could be a vapor retarder, but it's going to be somewhat vapor permeable. We don't want something that doesn't let any water through, like polyethylene plastic or vinyl or certain peel and stick products. Probably we don't want those, although you could probably get away with it. I'll talk more about that when we talk about vapor. And we're going to run that over top, and then we're going to run it down the front, and so that is our air barrier. That's one of our air barriers. We have a second air barrier in our roof. So we have two air barriers in our roof and one air barrier around our parapet and down our wall. And then you see there actually may be a problem. Well, actually, I'm not going to get into that. Okay, we'll hold off on that. All right, so by making our building airtight, we've done a couple of things. One is we've prevented hot air from coming in the summer. Two is we've prevented cold air from going in the winter. But probably just as importantly, maybe even more importantly, water, it can come in 3 different ways, and most people confuse the second two. So the first way is rain, and I think we all kind of understand intuitively how water might come in through rain. But the second way water comes in is through humidity. And so you can picture each water molecule as having a backpack, each air molecule as having a backpack with water in it. And so what's going to happen is water is going to want to come through with the air into these spaces. And actually, the humidity, that's supposed to be and it's going to want to come through here as well. And at each point, it's going to hit this air barrier, either this first one here or the second one, or there's only one air barrier on the rest of it. It's going to hit that air barrier, and it's not going to be able to go any farther. And that's going to come into play when we talk about vapor, because what happens is when humid water hits a cold surface that doesn't let water pass through it, it condenses. So if humid water hits metal, or if humid water hits glass, or if humid water hits plastic, vinyl, anything like that, and that vinyl, plastic, metal, or glass is cold, then there's going to be condensation on it. More on that in a little bit. The third way water moves through a building is through vapor migration. And vapor migration is both completely different than humidity and air. So humidity and air happens when there's air leaks, there's water leaks basically. So if there's air going into a cavity, there's water going into a cavity by humidity. Vapor migration is water moving kind of molecule by molecule through a solid. So you could imagine right now if I told you to build a wooden box, and I said, okay, build a wooden box, and I put it in a very humid room, and I drilled a hole in that wooden box. Because there's air leaking through that hole, the humidity from the room would also go inside of the box. But if I didn't put a hole and I made the box airtight, you can imagine that if I spilled water on the top of the box, that eventually, it may take a couple hours, it may even take a day or two, but eventually there'd be a water stain on the bottom of that piece of wood. So on the ceiling inside the box, there might be a water stain. Now that water moving through very slowly, often water moving through the box, through the enclosure of the box, that's the process of vapor migration. Different than the hole that we built for humidity, it's vapor migration. All right, so now we have our air tightness. Now the next thing we want is we want to have insulation. We want to have thermal resistance. So somewhere between the air barrier and on the roof, somewhere between the air barrier, we'll do that one in pink for obvious reasons. Somewhere between the air barrier and the roof membrane, we're going to have insulation. Oops, I need to do that on a new layer. All right, somewhere between here, we're going to have insulation. And in order to make it more airtight, we're gonna use 2 layers of insulation, and we're going to stagger the seams of those 2 layers of insulation, both vertically and horizontally. And that way, we can prevent air from moving through even better. So if air does leak through that first green layer right here, if it leaks through that first green layer right there, then at least it has to kind of wind in between. We're making it more difficult to get to here because we don't want the air to get to here if we don't have to. to get to the underside of the roof. More on that in a little bit. All right, so so then we also want our insulation on the in the cavity. So we use, again, rigid insulation. It can get wet for a little while, once in a while, not too big a deal. And oftentimes we can use sheets that have like a little key like this, so that we can take advantage of the lapping element. So each piece of insulation kind of has a little element that laps down over the other one, over the one below it. That way we can promote water in the cavity. We can promote it to go down the cavity and out to the weep holes before it actually gets to the, the waterproof layer proper. So I'll go ahead and I will I'll poche these, and then also we have other options. Because we have a situation where you can see there's a thermal bridge at the parapet. So we want to be able to have some insulation maybe in the parapet, and maybe even some insulation down here. Now, depending on how cold your climate is, this could be problematic. If you have insulation in the cavity and only a tiny bit of insulation outboard of the cavity, and you're in a cold climate and you have a humid environment, that actually can be problematic, but it's complicated. This stuff's actually quite complicated. All right, so now we can turn off the layers. And you see we have kind of continuous insulation, more or less. So we have continuous insulation. We have, and we don't worry too much if there's a little thermal bridging, like right in here where the drain goes down, because you have to have a drain. So a tiny bit of thermal bridging is not a big deal. We just want to minimize it as much as practicable. All right. Now, you remember I said that anytime water that's suspended in air as humidity hits a cold surface, that water is then going to condense if that cold surface is plastic or glass or vinyl or metal or something that water doesn't move through. And so if it's winter time and it's 0 degrees outside, and inside it's 70 degrees, then what's going to happen is that 70-degree air can hold more moisture. Think of the air as a glass that can hold a certain amount of moisture, and 70-degree air is a pretty big glass. It can hold a lot of moisture, and a 0-degree air is a little glass, like a shot glass. It can just hold a little bit of moisture. So if the 70-degree air moves through and hits the inside of this very cold wintertime roof membrane, then moisture will condense right here. So let me pick a different, I'll do like some kind of purple. Moisture will condense right here. So basically we want to limit the amount of air that's coming through to the roof, but we recognize that some will get in. And so we've, number one, used rigid insulation that is maybe not waterproof, but certainly is water resistant and can handle being wet once in a while. And we've used an air barrier here, probably that allows a little bit of moisture, a little bit of vapor to go through. So at the kind of molecular level, it will eventually dry out. It may take a couple of weeks if it gets wet, but it will eventually dry out. And a couple of weeks is actually not that big a deal. It sounds awful, but it's not that big a deal. When you get more than 6 months, it really starts to become problematic. Likewise, right now we have air. You see here, we have this air that's moving into the parapet, And this is actually not that uncommon a problem, because if it's 0 degrees, that parapet, at least the steel in that parapet, if it's metal, is going to be thermally bridging. So the cold from outside is going to be coming in, and that metal element is going to get cold, and the humid air, because this is a big glass, is going to hit that metal element. And what happens when warm humid air hits a cold surface like metal that doesn't let water through it, is there's going to be condensation. And I have, in a minute, I'll show you, I have an example of what that looks like in practice. But so we don't want air to go in there either. So we'll go back to our insulation layer, and we'll go back to our pink, and we'll use closed cell spray foam. And I think most of you guys know what that looks like, but I have a picture of that later too. But we use closed cell spray foam in here. Well, maybe not in there, but certainly in here. And that will prevent air, because closed cell spray foam will act as an air barrier and a thermal barrier. And that will prevent the humid air from going up into there to begin with. So that's a pretty good little trick to share with you right there as well. All right, now likewise we have this guy right here, where we have air that's going to move through the wall. And aren't we afraid that it's going to condense? Because this element right here is a rain barrier. So water can't go through it. It's a rain barrier. It's, in our example, it's our truck bed liner, and it can't go through it. And so aren't we afraid? Well, because of this exterior insulation here, then this bed liner roll-on or spray-on fluid applied waterproof layer and airproof layer is not going to be cold. Even though it's 0 degrees outside, that's going to be not so cold. If it's not cold, there won't be condensation on it. So by putting that bed liner, we've essentially said, okay, we're going to make something in the assembly that's going to keep it dry, and we're not afraid of condensation on that surface because we've added insulation outboard of it, and so it's not going to be too cold. It's going to be closer to room temperature. And remember, the condensation doesn't happen just when it hits metal or glass. It's when warm air hits very cold metal or glass. Now, does that work in the summer? Sure. If it's 100 degrees outside and 70 degrees inside, now the condensation from the 100-degree humid air, it's going to be a really big glass, so it can hold a lot of water. That air can hold a lot of water as humidity. And that 70-degree big glass is going to go and work its way in, and it's going to want to condense on the outside of the what I'm calling the truck bed liner. And it's going to, because that bed liner is cold, it's 70 degrees inside. And so if it does condense there, are we afraid? Hell no, we're not afraid, because that bed liner was made to keep rain out. So it certainly can keep occasional condensation out. And so that condensation will eventually either just dry out through evaporation, or it'll just drip down and get redirected outside the building via flashing and weep holes. All right, so now we've handled rain, we've handled air, we've handled thermal, and we've handled vapor. Now on the roof, there are 2 air barriers. There's this one right here, and then there's the rain barrier that's also an air barrier. But in the wall over here, there's one layer, and that layer serves as an air, vapor, and rain barrier. So that's part of the confusion people have. I think the 2 things people get most confused about is you'll call something an air barrier like we have here, and this one is vapor permeable, hopefully. Because we don't want moisture to get trapped in there, because it will eventually get in. So this idea of a vapor barrier is crap. It's based on 50-year-old research that was never very good anyway, that was only applicable to old buildings that were leaky, and really was only applicable to cold climates. And so the idea of a vapor barrier is not really a thing anymore. It may still be a thing in NCARB world, and if you see a question about that, then just make sure to put the vapor barrier on the winter warm or the warm side of the insulation right up against the insulation. But This is how it should really be detailed. Now, the older parapets were not detailed like this. They didn't have our plastic products, they didn't have our building science, and so that's one of the ways, there's lots of ways older buildings are better than newer ones, but older ones leaked all the time from rain. And newer ones have condensation in the structure all the time from this guy right here from the air. All right, now let's go back to our slideshow. And so this is what, if you were curious, this is what spray foam insulation looks like. And you can see this is closed cell, it's kind of shiny. It doesn't want to let air through. And that's good because we don't want it to get into the parapet. So this is the metal structure of a parapet. We're looking inside the parapet. And because cold air, because it's uninsulated on the right-hand side, it's very cold in here in this parapet, and the warm, moist air from inside the building works its way into the parapet and then hits the cold metal and then condenses, and it can cause all kinds of problems. If we have two layers that are not moisture permeable, that don't have enough perm, that are not vapor control layers, but rather vapor barriers, like if the inside we have vinyl wallpaper, say it's a medical clinic and we need vinyl wallpaper because it has to be easily cleaned, and on the outside we have the kind of truck bed liner that I told you about. So when moisture gets in, it cannot dry to the inside and it cannot dry to the outside. And maybe we're in a place where we have a sprinkler system and the sprinkler is set so one of the walls is being sprayed every morning by the sprinkler, and so it's always getting wetter and wetter and wetter, and some of that moisture is working its way into the wall cavity, but it can never get out. So we never want, from vapor control point of view, the most important thing is to not have two layers that are vapor impermeable. You can have one that's vapor impermeable and one that throttles the vapor, that slows down vapor, but you don't want two that are vapor impermeable. That's why our air barrier on the underside of the insulation on the roof that we just drew, that's why it allows vapor to move through. And again, vapor is moving it through. Vapor is moving through at a very kind of slow trickle. All right, so now let's take a look at our. Not sure why this is behind. I don't think my next slide is actually up on your screen yet. I'll wait a second. There you go. Now let's take a look at next week's problem. Next week's problem, we're going back into kind of pro-practice world. We bounce back and forth between the two. And so it says the architect hires a civil engineer to design a church parking lot. Required to address stormwater runoff, the engineer selects an off-the-shelf under-pavement tank to hold the runoff and slowly release rainwater back into the ground. The engineer relies on the manufacturer's literature, which was not written by an engineer, though the civil engineer didn't know that, to write the prescriptive specifications for the buried tank. The contractor who bid on the project, and by doing so agreed to build it both perfectly and to build it as it was drawn, expressed concern that the tank would not perform properly because it sat above the water table. I should say it sat below the water table. I should say below the water table. The contractor submitted an RFI expressing the concern through the architect to the civil engineer as is required, and the civil engineer responded through the architect to the contractor as is required with a dismissive, "It's fine, install the tank as it was drawn despite your water table concerns." The tank was installed as drawn, and it caused a parking lot collapse that delayed the church's opening by 16 months and cost a lot of money to fix. Choose who is at fault. Is it the manufacturer because the tank was not adequate? Is it the architect because the drawings were not adequate? Is it the civil engineer because her drawings were not adequate? Is it the owner because of the Spearin doctrine, which holds that the contractor isn't responsible for faulty drawings? Or is it the contractor because he warranties that his work won't collapse? That is our assignment for next week. Now, as always, you can peel off now and get to work, or you can stick around while I answer a couple of the questions that came from last week. Number one, and this one actually came from last night, we did an Ask Me Anything as part of the ARE Facebook group, and someone asked what the Spearin doctrine was versus the standard of care. The Spearin doctrine, and I said I will answer that tomorrow when I have some time to research it. The Spearin doctrine is based on a 100-year-old Supreme Court case, the U.S. versus Spearin, And it basically says that, look, the contractor has to build it perfectly, but if the drawings are faulty and the contractor has to build it to the exact agreement, the drawings are called contract documents because there's a contract. The builder has to warranty her work, and the builder also has to build it exactly as drawn. And what happens then, it's an impossible situation for the contractor because they can't warranty their work if it was drawn incorrectly. So if there is a faulty drawings, the Spearman Doctrine protects the contractor, and then it's actually going to be on the owner to fix it. And then of course the owner can sue the architect for the faulty drawings. The standard of care is the level of expectation of perfection that the architect is held to. It is way lower, thankfully, than the contractor, in no small part because the AIA, which represents architects, is the one who has managed to make their contracts the default. And the standard of care says that the architect is not held to perfection and does not warranty her work, but rather the standard of care says that she will make her drawings and specifications and instruments of service at a level at least comparable to what would be expected in her region at her time. So basically it's a race to the bottom sometimes, where basically you're saying, okay, how can am I doing a good enough job? Well, what do other people do? Well, you know, other people detail their parapets the way I have, and so even if it's faulty, if other people are doing it right now, I'm not liable. So that's the difference between the Spearman Doctrine, which protects the contractor against faulty drawings, and the standard of care, which protects the architect against the expectation that the architect will do everything perfectly. All right, the second question was about panic hardware, and panic hardware looks like this, and it allows so that the idea of panic hardware is if there's a fire or some kind of an emergency, and everyone rushes to the exit, or even though this one says not an exit, everyone rushes to the exit, and if it's pushing so hard that the person can't back up far enough to be able to, the person in the front of the pack, the mob, can't back up far enough to open the handle, the bar itself will push in and the door will open. And you guys have all seen these. And where they're required in they're required in assembly occupancies that are over 50 people. They're required in, it's taken a while. You're not seeing pics because it's taken a while. Sorry about that. That's a Zoom issue, that's not a me issue. It'll come in a second. Panic hardware is required in assembly occupancies, so things like lecture halls and theaters with more than 50 people. It's required in educational settings, so K through 12 in daycare when there's more than 50 people, an occupant load of more than 50 people, and it's required in high hazard, as you might imagine, when there's more than 50 people. That's when the panic hardware is required. The second question, now it finally went, I went back to the old slide. Oh, there we go. The second question, so that was the panic hardware. Let's see, there it is. That's what the panic hardware looks like. The second question, third question I got, my neighbor, I love this question. My neighbor just installed solar panels. He also placed them on the north gable of the roof. I want to tell him so bad he wasted that money. Michael, can I tell him that? Yeah, you probably can. I mean, eventually solar panels, photovoltaic panels are going to get cheap enough that it's probably worth putting them on the north face, but you know, on the north face, I don't know, maybe it's 5 or 10%. The output is what would be on the south face. So what he should have done is put them on the south face of your roof and his roof. That would have been a better thing for the environment. So you can absolutely tell him that he wasted his money. But you know, the problem with people who try things, the early adopters, is that kind of like I told you so makes people hesitant to be early adopters, and we want people to be early adopters in solar panels. So maybe you can just kind of tell your roommate or spouse that that person wasted his money, but maybe not tell the person. The next question is 15 degree the tilt of the Earth on the plane of the orbit? No. At the equinox, which we're coming up on in about 2 weeks, the Earth is perpendicular to the sun. So the core of the, the center of the Earth, if you made a line from the center of the Earth to the equator and you extended that, it would eventually hit the sun. But on the solstices on June 21st and December 21st, when the Earth is tilted at its most, the Earth is tilted 23 degrees. So that 15 degrees is just kind of an optimal summer only or winter only angle. You add 15 degrees. So in the summertime, in the wintertime, you add 15 degrees. So if this is year-round performance, when the sun is low in the winter, you're going to add 15 degrees to your angle, and when it's higher in the summer, you're going to subtract 15 degrees from your angle of your photovoltaics. Those of you who were here last week know what I'm talking about. And finally, it says, guys, do we need to read through all the case studies, or can we start with the questions directly during the exam? Maybe we can save more time. Absolutely. There are people feel very strongly about this, but I happen to feel very strongly that that you do the case studies last because they take longer, and you don't want to run out of time. And sure, you may see some things. I know this wasn't what the person was asking, but sure, you may see some things in the case studies that are useful for some other thing you found in the exam, but that's fine. You can go back later if you have time and fix it. People, especially in PPD and PDD, especially PDD, people run out of time all the time, and you do not want to run out of time. So because you don't want to run out of time, and because if you have 10 questions per case study, you're going to have 10 or 11 questions per case study. If you have, say, 10 questions per case study, 5 of them you can answer without checking the case study typically. They're just things you already know. You don't have to check the case study. So you'll answer those 5 and trust yourself. If you're running out of time, trust yourself. If you have plenty of time, then you can look it up. Then you can use the search bar to search for the other 5. And so you definitely want to search for the most obscure term that will get you to your answer. So if the question is about how many parking spaces you need for a farmer's market, you don't want to search parking because that'll show you all the zoning code related to parking. If instead you type in farmers, you'll find the one place in the excerpt that they've given you of the zoning code that says farmer's market, and then you can quickly find out how many parking spaces are required for the farmer's market. So I highly recommend not reading through the whole case study. Frankly, the case study, reading through the whole thing, would take you probably an hour unless you're a really fast reader, and I don't think that's a good use of your time. And it's a reference document, so even if you read it all, you're not going to remember how many, you're unlikely to remember how many parking spaces you need for a farmer's market until you actually come across that question. So start with the question. So read the summary of there's like the first page of the case study is a 2/3 of a page summary that says it's a farmer's market, it has an indoor component with bathrooms, it holds this many people, occupancy classification is such and such. And so you'll read that first, and then you'll read the questions, and you'll go back to the case study as needed to look at the to use a search function to find out the answer to what you've just read.
I have a question, Michael.
Yeah, what's your question?
You pulled this up yesterday from the Amber book.
Uh-huh.
One of the questions on the flashcards was, can you build on a floodplain?
Mm-hmm.
And I don't think the answer is no, right?
Yeah, so this is a difficult question. I've been doing some research on it. I've called a bunch of people. I cannot find any rules that you can't build on a floodplain that are kind of national. Now, in the zoning of a given town, it may be that you can't build on a floodplain. But with regard to the FEMA stuff, I can't find it. I can find that there's different insurance rates for flood insurance and that kind of thing, but depending on your base flood elevation. And so I think from an insurance point of view, it's probably the thing that limits you from building it. And you're going to have to build over what's called base flood elevation, which means your first occupied floor, like a non-garage or whatever, has to be at a certain height based on your FEMA flood maps. but I think that's more for insurance, which I guess kind of means it's required, but I don't think it's required as part of any kind of nationwide rule. Does anyone know differently? Please speak up.
Yeah, but more airport is actually built over the floodplain.
Say that again?
LaGuardia Airport
Uh-huh.
is actually built over the floodplain.
Okay. The indoor part or the outdoor part?
The actual terminal.
Okay. Yeah. All right. So there you go. So you certainly can build on a floodplain. Now, the height of the terminal, the height of the bottom floor of the terminal may be above base flood elevation. Do you know the answer to that?
No, it is actually the flood goes up 100 years. Flood goes up to the second floor.
Okay.
So the design of the building has a roll-up gutter that goes in and out, and also we designed the power plant to be waterproof.
Okay.
With some barriers of it.
Yeah.
Water barriers.
Yeah, so you can, I guess you can technically build on a floodplain. I can't find anything that says you can't, and if you Google it till you're blue in the face, you won't find anything that says at the national level that you can't build on a floodplain.
I don't believe that's correct. I don't believe that you can build
good,
on
a
a
debate.
floodplain currently. I believe that LaGuardia was built many years ago, and the floodplains have changed because the roll-up flood barriers and all that sort of stuff. I've done that with New York City Public Schools as well, but these are existing structures.
Yeah, I mean, okay, there's a couple of different things because you definitely can build on a floodplain only because if you couldn't, no beach town would exist. So, you know, your typical beach town may be 3 to 4 feet above sea level in the houses, and they could still build on them. You just have to build the first floor high. So I'm pretty sure you can always build on a floodplain. Now, you may not be able to build within a certain distance of a wetland or something like that. There are rules, there are EPA rules about that, but I don't think you can't build on a floodplain. But it may be that you can't build where the bottom floor is below the base flood elevation on a floodplain.
Yeah. Actually, LaGuardia is a new building, but most of the houses also in Connecticut, they are over the floodplain. So what they do is actually they jack up all the buildings, the houses.
Yeah, interesting.
That's really strange because I know in Pennsylvania we had a series of houses that were built within the floodplain, and the feds came in and actually purchased the houses from the owners and destroyed them.
So that's something very specific. So yes, so that's just more than just a floodplain. So first the one by one, in the 50s or 60s or 70s, the insurance companies stopped covering you for flood. And the reason they stopped covering you is something called correlated risk. So insurance companies want to make sure that they cover everyone for everything because they can make more money doing that, they can charge you more. But they don't want a situation where everyone has to file a claim at the same time. So they'll cover you for something like a fire in your house, but if there's like a war and the whole city gets firebombed, they will not cover you because they know that the insurance company would surely go out of business if everybody said, I need you to pay me at once. So the insurance companies, one by one, stopped offering flood insurance, but we still wanted, as a nation, flood insurance to be available. So the federal government started offering flood insurance, and unfortunately, it's what's called a moral hazard because the rates for the flood insurance are much lower than they would be if it was a free market. So in other words, your risk of flooding in a certain place, like in that place in Pennsylvania, may be much higher than what you're really paying for. And the reason for that is because if your flood insurance rates go up too much, and this is a big deal right now with climate change, if your flood insurance rates go up to really reflect the risk, then people start writing to their congressman, and then the congressmen start talking to the flood insurance people, and they get mad. So there's enough political will so that we really have kind of a market failure, especially as it relates to the 40 million people or so who are going to have to move inland over the next 30 or 40 or 50 years if we don't do something dramatic. Now, within that flood insurance, it is not unusual that the same house or building, but usually house, will flood sometimes 5 times. So it'll flood, and the feds will pay their insurance and pay it out, and it'll flood, and it'll pay it out, and flood and pay it out. So if it happens, say 5 times in 2 decades or something like that, which is not, it's not unusual, I mean, it's not typical, but it's not crazy, it does happen, just because of where a building was built, because the FEMA maps didn't account for it, or it's an older building that predates the FEMA maps, then the feds will come in and they'll do exactly what you described in Pennsylvania. They'll buy out all the houses and relocate the town up on a bluff and destroy all the houses, because it is cheaper for them to buy all the houses than to pay out $250,000 per house in flood damage every 5 years.
Hi Michael, I have a question on actually this detail as well. So I've seen details where we don't have a vapor barrier at the roof, and I think we touched on this when we were going through the detail, but I was hoping you could elaborate on it a bit more.
Yeah, so what we have there is really not a vapor barrier, it's an air barrier, and you could get away without having it if you have a climate that doesn't get too cold. That may be one way you can get away with it. Another way you can get away with it is you can make, if it's done correctly, this thing is so watertight, because if it's any leaks, then the membrane itself, the roof membrane, is so watertight that if there are any leaks, you will know about it and it will get repaired. And so in theory, there won't be air moving through at all because it has no place to go. It can't leak out there anyway. And also, the fluting, the metal fluting acts as an air barrier if you seal it, and the sheathing that's on top of it, if you just had that, if you seal that, although it's a little difficult to seal because of the fluting at the seams, it may not be quite even. One thing I did forget to mention that now I'm noticing I forgot to mention is that underneath the membrane, immediately underneath the membrane, we're going to put a board, as a board product, kind of like a cover board or underlayment board, has a name to it, I can't remember. But we're going to put that there because otherwise, without it, because this rigid insulation isn't that rigid, and because people with boots who are walking on roofs can be pretty heavy, and if their heel digs in, then it's going to make a divot here, and then when the water comes down, it's going to fill up here, and there'll always be mosquitoes, and it may even tear the roof. So in order to get a nice, clean, solid surface to attach the membrane to, we're going to put a second kind of layer of board on top of the insulation. And frankly, a lot of times the insulation comes with that OSB or whatever built into it as well. So that's your answer, is that you can get away without doing it. It's sometimes done, but most of the smart people I'm reading say that there ought to be an air barrier to reduce it. Again, especially in a cold climate. If you're in a mild climate and it really doesn't get below 50 degrees, there's just not that much condensation that's going to happen here, because it's maybe never, depending on how humid it is inside. There just might not be that much moisture on the air that it's going to be that cold anyway.
Okay, thank you. And then does that also apply to concrete decks?
So with concrete, you can actually seal the concrete. With concrete, you can actually seal the concrete, and that itself, especially the little holes that are for the, God, I'm blanking on all the names right now. My brain's not working. Help me, the form tie holes. If you seal up the concrete, that can be the air barrier. So you won't need this green layer, because this green layer will be provided by the concrete itself.
Okay, great. Thanks so much.
I have time for one more.
Yeah, I have a question, and I'm wondering if maybe this is just actually a whole different conversation, because this parapet detail is something I've seen it's very common, and I'm curious, let's say this roof is actually an occupiable roof, so you have another story above, and because of the way that you're designing the cladding, you actually want the parapet to be level with the roof deck, and then you want to have a guardrail. Is that something you've seen before?
Yeah, so when the best way to deal with that is to, there are things called, and you may know this already, but there are little adjustable elements called deck stands. They're like kind of plastic and adjustable, and you can screw them and unscrew them. And so you put those every so often, and I'll show you in a minute what those look like. And then on top of that, you can put sleepers, and on top of the sleepers, you can put, you know, you could put your wood elements. You know, if you're kind of doing a boardwalk or, you know, kind of wood porch type roof deck, or you could put stone elements or something like that. And then so the water goes through, and then it's pretty much a standard. It's pretty much standard under that. So the weight of the deck is distributed to enough different places on the roof that it's unlikely to tear the roof membrane. Well, thank you everybody, and I hope you have a great night. I have a sign off that I forgot. It's good night, get licensed.